All right, let's just jump right in. There is a huge, huge problem at the very heart of physics. I'm not exaggerating. It's this fundamental conflict, like a real clash of the titans between our two best theories of, well, everything. And it's what's holding us back from having one complete picture of the entire universe. So, in one corner, you've got general relativity. This is Einstein's masterpiece, right? It beautifully describes the grand cosmic dance of planets, stars, and galaxies, the really big stuff. And then, in the other corner, you have quantum mechanics. This is the weird, wacky, but unbelievably successful theory for the super tiny world of atoms and particles. And here's the thing. Each one is basically a world champion, but only in its own weight class. And that right there is the core problem. Think of it like this. Physicists have these two amazing toolboxes, but when they try to pull a tool from the general relativity box and one from the quantum mechanics box to work on the same problem, the instructions just don't make sense together. The rules clash and the whole thing falls apart. They're just incompatible. So let's really dig into this great divide. I mean, why can't our two best theories of the universe just play nice? Okay, so general relativity paints this incredible, elegant picture of gravity. It's not some mysterious force reaching out and pulling things, no. It's actually mass and energy, like our sun, literally bending and warping the fabric of space-time itself. The reason we orbit the sun? We're just following the straightest possible path through that curved space. It's beautiful, it's elegant, and for all the big stuff in the cosmos, it works perfectly. But then you zoom way in, and you get to the quantum world. And down here, man, things get weird. Nothing is smooth and predictable. Everything is kind of fuzzy, existing in this weird cloud of probabilities. Energy isn't continuous. It comes in these tiny, distinct packets called quanta. It's like reality itself is a bit blurry up close. So you're probably thinking, okay, so what? One theory for the big stuff, another for the small stuff. What's the problem? And that's a fair question. The problem, the big deal, is when the universe forces us to use both theories to describe the very same thing. And to really get why that's a problem, we need to look at where these two theories are supposed to meet. And that brings us to the fundamental rulebook of the universe, the four forces that run the whole show. That's it, just four. Think about that. Every single thing that happens in the universe, from a star exploding to your phone charging right now, it's all governed by just these four fundamental forces. And here they are, the Fantastic Four. You've got gravity, the one we're all familiar with. Then there's electromagnetism, which is basically what powers our entire modern world. And then there are the two nuclear forces, the strong and the weak, which are the bosses inside the nucleus of every atom. Okay, now here's where it gets really interesting. Physicists have actually figured out how to describe three of those forces, electromagnetism and both nuclear forces, with the exact same set of rules, the rules of quantum mechanics. They all fit together perfectly in this amazing framework called the Standard Model of Particle Physics. You can think of it as our ridiculously successful parts list for the universe. But gravity? Gravity is the rebel. It's the odd one out. It's like the wallflower at the quantum party that just refuses to dance. It will not be described by the same quantum rules as the other three. It insists on playing by its own, completely different, relativistic rules. And that, right there, is the source of the whole conflict. So where does this actually matter? Let's take a trip to the most extreme places in the universe. Places where this isn't just some academic debate, it's a full-blown crisis, where our understanding of physics completely shatters. I want you to meet this singularity. This is a point in space and time with a density so insane, so unimaginable, that the beautiful equations of general relativity just break. They go completely haywire and start spitting out answers that make no sense, like infinity, infinite density, infinite gravity. The theory literally just throws up its hands and says, I give up. And where do we find these cosmic system crashes? Oh, just in two of the most important places we can possibly think of. At the very beginning of the universe, the Big Bang, and right smack in the middle of every single black hole. To understand what's really going on in those places, we desperately need a single theory that can handle both crushing gravity and the tiny quantum world at the same time. But the problem isn't just with things that are infinitely big and dense. It also pops up when we do the exact opposite, when we zoom into the smallest possible scales imaginable. And here's the other side of the coin. See, for general relativity to work, spacetime needs to be a smooth, continuous sheet, like a trampoline. But quantum mechanics says no way. It predicts that if you could zoom in to the tiniest possible level, what's called the Planck length, spacetime is actually a boiling, chaotic, turbulent mess, a quantum foam. So one theory says smooth, the other says chaos. They can't both be right. So our best theories fail us in the most important places. What do we do? Well, the search is on. This is the quest for the holy grail of physics, a single theory to unite them all. And that holy grail has a name, a theory of quantum gravity. The goal is right there in the name, to finally create a single framework where quantum mechanics and gravity can shake hands and work together, to give us at last one coherent story of how reality works. So how do we even begin to build something like that? Well, the general idea involves a few big steps. First, you have to try and quantize gravity, which is a fancy way of saying treat it like the other quantum forces. And if you do that, it means gravity has to have its own force-carrying particle, the graviton. Then, to make all the insane math actually work out, a lot of physicists turn to this incredibly powerful idea called supersymmetry, which just might be the missing piece of the puzzle. Yeah, this hypothetical particle, the graviton, is really the key. If we could find it, it would be the smoking gun, the little quantum packet of gravity itself. It would prove that gravity can play by quantum rules. We think it would be massless and zip around at the speed of light, but the force it carries is so mind-bogglingly weak that finding one is, well, let's just say it's a monumental challenge. And that's where this wild idea, supersymmetry, comes back into play. Now, the details are super complex, but the main idea is that every particle we know has a secret super partner we haven't found yet. And why is that so cool? Because if you use that idea in your calculations, something magical happens. When you trace the three quantum forces back in time to the super high energies of the Big Bang, their strengths all seem to meet at a single point. It's a huge hint that they were all once a single unified force. And think about what that implies. If three of the four forces were once united, it's not a huge leap to think that maybe, just maybe, gravity was right there with them in the beginning. Supersymmetry could be the mathematical key we need to finally unlock that door and create one beautiful system that describes all four forces together. And you have to understand the stakes here are just immense. This isn't just about making our equations look tidier. Finding a theory of quantum gravity is, in a very real sense, an attempt to see back in time. It's our best shot at understanding what the universe was like in its very first moments, at the instant of creation itself. So that leaves us with the ultimate question, doesn't it? Are we getting close to finally cracking the universe's source code? Could a theory of everything, one that explains our entire universe from the Big Bang to black holes, actually be within our grasp? The honest answer is, we don't know. But the search for it, that is, without a doubt, the greatest adventure in all of science.